Hello. So first of all, I also want to thank warmly the organizers for inviting me to participate to this nice conference. And it's a real honor to present. Sorry? Oh, thank you. And it's a great honor to be able to present a little piece of work here. So what I'm going to tell about is something is extremely related to some works of Hubert that were mentioned several times, namely exact calculations in out of equilibrium settings in quantum impurity models. So, and essentially I will talk about a single model, the sine-Gordon model, the boundary sine-Gordon model. So, this is the outline. I will briefly introduce quantum impurity systems, just to remind to those of you who are, just to set up the stage. And then I will describe the solution that was obtained more than 20 years ago by Hubert and collaborators. And the second contributor in this room, namely Paul Fenley. And Andreas Ludwig is the third culprit. And then I will move to the presentation of new results in a regime that was not addressed previously in this boundary sine-Gordon model. And finally, I'll present you some recent experiments which actually are the motivation for this work, showing quite good agreement between the predictions and the measurements. Okay, so quantum impurity models is a very large class of problems. So very roughly what we have is extended systems, homogeneous extended systems, gapless. So you can maybe think of them in the simplest case as free fermions, for example. And those extended systems are coupled at one point in space, which is an inhomogeneity, where they interact. So here I depicted an impurity. It's dirty, okay, but this object here, the impurity, doesn't need to be a quantum system. It can also be an interaction between the two systems at one point. In other words, we don't necessarily have degrees of freedom living on this impurity. This kind of setting is very naturally forced out of equilibrium by choosing different equilibrium states, macroscopic equilibrium states for two or several baths. And due to the connection between the two subsystems or more subsystems, something will flow from one reservoir to the other one. And natural questions are, how can we characterize this non-equilibrium state? Okay, so indeed it's a very, very large class of systems, and we will have, I will shortly restrict this class to a very specific model. Just to quote, it's difficult to talk about quantum impurity models without quoting the Kondo models. So this is a huge family of models labeled by the symmetry group and the representation. Another prominent example of quantum impurity models is the boundary sine-Gordon model. And there are many, many possible generalizations of this with several bosons, as we heard about 2 days ago. And the list is obviously infinite. Okay, so what does characterize those quantum impurity systems out of equilibrium is that they mix two things that are quite difficult to cope with. First, interactions, and in all interesting cases, the interaction is a relevant one, so it means there's a flow towards strong coupling, defining an energy scale which I call TB, which is called TB in this talk. It's a reference to the Kondo temperature Tk. Okay. And to that, we add the fact that we are out of equilibrium, and the net result is that we have no control field theoretical tool to address this question. Nevertheless, it's a very interesting, those are very appealing systems to study for many reasons. Maybe the first reason as theorists is that they are good time models where to learn many things. In that respect, for example, the Kondo model was the test bed for Wilson renormalization group, as you know. So they play a role also as stimulating the theoretical understanding of more complex systems. On top of this, they are also experimentally realizable. We can realize them experimentally. Okay, so it's quite easy to, it's quite a common situation to have a gapless extended system connected at one point in space. I will later present some examples of this. And last, this makes also them interesting. They are very often integrable. Okay, so there are two features I want to emphasize. First, this integrability. Integrability is usually in condensed matter a fragile notion. The moment you want a system or real physical system to be integrable, you have to fine-tune many parameters to achieve integrability. For quantum impurities, it's the restriction, the conditions are less stringent for the reason that you can find, well, generically, if you put yourself in the scaling limit, so if the experimentalist has a knob to turn and can decrease the coupling to the to the impurity, then the scaling limit can be reached, and in good cases there is only a single relevant operator, and the system is generally integrable. Of course, there are corrections to this if you go to high energies. Okay, and the great idea Hubert, Paul Fendley, and Andreas Ludwig had was to exploit this integrability to produce an exact solution out of equilibrium. Okay, so now I will focus on a single model, namely the boundary sine-Gordon model. So you probably all of you know this model, but I remind its definition. So I unfolded the system. So we have a chiral boson living on the whole line, and it's coupled. It's interacting at one point, x equals to 0, via cosine potential. So we will shortly switch this. So there are two parameters here. Look, the gamma here is the bare coupling, the one that will flow to strong coupling. And the beta labels the different kinds of models, of sine-Gordon models. So there's actually, the physics is quite different when you vary beta. And the relevant parameter is this parameter. So it's 1 over the scaling dimension of the cosine term minus 1. So this lambda will play a crucial role in what follows. So remember, this lambda labels, well, it's a way to encode the beta. Okay? So this model is nice because it's minimal, it's very simple, okay? It's the simplest, maybe the simplest model we can think of with a continuous symmetry. It also offers a straightforward way to implement out of equilibrium forcing, because there's this U1 charge, so we can simply couple to it, okay? And it's not a very big surprise. As a minimal model, it has many realizations. So I will quote a few of them. It describes tunneling between liquid and liquids, tunneling between fractional quantum Hall effect edge states. Well, with some limitations, I will be not all the FQHE is possibly addressable with the sine-Gordon model, but at least some of them. We heard a talk by Ananda Roy a few days ago, who was also advertising the fact that it describes an array of what it can describe nanocircuits, like an array of transition junctions. It also describes tunneling in a resistive environment, or quantum Brownian motion in a cosine potential, where the out of equilibrium forcing is a tilt in the potential. And this is the key point to this work. This model is integral. Okay, so what are we going to do with it? Well, first I will review the solution Hubert and co-workers have obtained on this model, which is namely an exact solution out of equilibrium. And in particular, it describes, amongst other things, it describes the nu equals 1/3 tunneling. Well, the tunneling between a nu equals 1/3 states. Okay, so how I will review this solution. How is it possible to use integrability to solve this model? So you start with your two wires. Say you want to study, for example, tunneling between liquid and liquids. And the Hamiltonian, as I said before, several pieces. One first piece is the free Hamiltonian describing free bosons. The second one is a boundary term, namely the boundary sine-Gordon term. And last, the last term is the forcing out of equilibrium. By a simple mapping, actually defining the difference of the two bosons as the odd boson, we end up with a theory with a single boson, which is integrable. And the next question is what to do with this, how to deal with this out of equilibrium. So the main idea is to use integrability to identify the correct basis where this many-body problem with this nonlinear interaction term becomes, it won't become linear, okay? It's not a mapping to a free system. It stays, the interaction is still here, but it is possible using integrability to find a basis where everything factorizes. Okay, and the trick to do that, the wonderful trick, is to actually take a more complicated model. You take the boundary sine-Gordon model and you add a bulk sine-Gordon term, giving a mass to the spectrum, and at the end of the calculation, you send this mass to 0. So this trick allows to pick up exactly the right basis that will diagonalize the scattering on the impurity, and introducing the Zamolodchikov-Fateev modes, which I call big A of theta, where theta is the rapidity. The boundary scattering factorizes into single quasi-particle events, each of them being described by the R matrix, the boundary S matrix. Okay? So this way you can construct scattering modes. So those modes are create eigenstates of the full Hamiltonian H0 plus HB, so the boundary sine-Gordon model. So at that stage, you need to go further and incorporate the forcing. And what you want to do is represent the bath, the original bosonic bath, there's 3 bosonic baths in this case, in this quasi-particle basis. Okay? So natural question is whether it's possible. The general answer is no. You need more. You need several. You need strong conditions to be able to represent the original biased reservoirs within this quasi-particle basis. But for the boundary sine-Gordon model, this condition is fulfilled. So the moment you can do that, you can determine the density of particles, of quasi-particles, describing your bath at arbitrary temperature and voltage. Okay? And you do this using the thermodynamical Bethe-ansatz. So it's a recipe, quite long recipe, but it works quite well. And at the end, what you have to do what you want to do is compute the current. The simplest, the first observable you want to compute is the current. And due to factorization of the scattering, you can decompose this current as one-body contributions. Each mode will contribute to the current. So you take, for each mode, you count how much charge is transferred, okay? And you will then weight this this charge transfer with the appropriate density that you extract from the TBA. So up to now, I didn't say a word about the spectrum, the nature of the quasi-particles. So generically, in the sine-Gordon model, you have always a soliton and an anti-soliton. They are charged particles. And in the so-called attractive regime, when lambda is bigger than 1, that is, the cosine term is relevant, well, more relevant than, the more relevant the cosine term, the more attractive the system is. And in this case, in the attractive case, you have additional states in the spectrum that are called the brothers. They do not contribute to the current. And finally, the current depends only on the soliton and anti-soliton densities. And the formula that was obtained is this very famous paper, or series of very famous paper, is very transparent. It's like a Landau-Böttcher formula, except the densities here are those of an interacting system. So those are not Fermi functions, right? So where does the interaction shows up indeed in the densities and also in the transmission probability of charged particles that is simply related to the boundary F matrix and continuously depends on lambda, the boundary the sine-Gordon parameter. Okay, so let me mention also that this is one way of doing things, but there is also an alternative approach that's been developed also around the same time. Namely, Bajanov, Lukyanov, and Zamolodchikov also solved this model out of equilibrium using totally different techniques. And well, it also works very well. It also provides an exact solution. Okay, so this works extremely well. So it's the second time you see this plot in this conference. So those are the the straight line, the black line is the TBA prediction, and the crosses are experimental data, whereas the boxes are Monte Carlo data. You see that everything well, it fits extremely well. Okay. And this example, this is given, this curve has been obtained experimentally in the tunneling between 1/3 states, edge states, okay? Remarkably, for this system, the value of lambda, which is 1/nu minus 1, is equal to 2. It is an integer. And this will play a role shortly. So why does it play a role? Because now I'm going to talk about an extension of this. Well, it's just a continuation of this work in the case where lambda is not an integer. And I will shortly explain why this makes a difference. So when lambda is not an integer, a new feature appears, which is rather annoying. Namely, if you look at the bulk S matrix describing the scattering between solitons and anti-solitons, you notice that there is a specific term, a reflection term, which I will tell more about in a minute, which is 0 when lambda is in an integer, but doesn't vanish when lambda is a generic number. Okay? So this amplitude describes the fate of well, you can view it as a scattering event between two particles, namely a soliton and an anti-soliton. So the soliton is red and the anti-soliton is blue. Okay, they have different momenta, and when they collide, they can either pick up a phase and continue their way, or they can exchange their momenta or the charges. It's the same thing, okay? So we have two terms. We have two possible events when lambda is not an integer. So why is that a big difference? It is a big difference because if one now looks at a many quasi-particle state, which I depict here like this, you see that, for example, this soliton, which is scattering in a gas of anti-soliton, will have the possibility to exchange its momentum with the anti-solitons it crosses. So this is one of the many possible paths it can follow. Okay, there are many different paths, and formally, what it means is that unlike the diagonal case where charge and momentum were living separate lives, here they are in some sense entangled. So you cannot disentangle charge from momentum. And a very annoying consequence is that you can no longer implement TBA. The reason is that TBA is obtained, as you know, you take in the following way: you take one particle, you impose basically that the wave function is single-valued, so you take one pick up any quasi-particle, you pass it around all the other quasi-particles of the systems, and bring it back to its original position, and it should pick up a phase which is a multiple of 2 pi. This is at the root of the thermodynamical beta ansatz, which allows you to determine the densities. In the presence of off-diagonal scattering, you can no longer do that, because if you pick up, for example, a soliton and you pass it around all the anti-solitons, there is a finite probability that it ends up as an anti-soliton. So what it means is that the monodromy matrix, the monodromy is actually a matrix. It's no longer a simple phase. And the only way, at least I know of, to derive the TBA equations is to diagonalize this monodromy matrix. So this has been done actually a long time ago. And many people contributed to this. Now it has become an art. So it's ABA, algebraic beta ansatz. Okay? And the net result of this procedure, this diagonalization procedure, is that you end up in a new basis, in a new many-particle basis, many-body basis. And so just to depict things, this situation with off-diagonal scattering is replaced by a new situation where all the scattering is diagonal. Of course, the quasi-particles are not the same. So they are nevertheless things that you can follow up from left to right. Things you can follow up are the big dots here. Those are the solitons and anti-solitons. In the new picture, they become solitons. And we'll see shortly that they have no charge any longer. The charge degrees of freedom is taken care of by a new set of quasi-particles, which are technically the string solutions of the that can be organized in strings, and some of them are charged and will carry charge degrees of freedom. So you end up with a diagonal theory again. So in practice, it's quite cumbersome actually, and if you want a finite number of quasi-particle, you need first a rational value of lambda. I have new batteries. I'm here again. Hello. So I have 40 minutes, right? No. Okay, so here's the spectrum, and as I was saying, the thermodynamical beta ansatz can be established, and this is the TBA diagram, which is not really readable from here, but you have several families. You have a new feature also that appears new, like the fact that the kernel is not symmetric. It's much weirder system than in the diagonal case. So one question can be, what is the connection with the diagonal system? Something I didn't mention, which is important, is that if you go to 0 temperature, even in the off-diagonal case, at finite voltage, you will populate only one species. Say you put a positive voltage, you will have only anti-solitons. Okay? If you have only anti-solitons, you kill totally this off-diagonal scattering. So you should recover the diagonal solution of FLS. And indeed, this is the case. If you look at the entropy that carry those strings, this entropy vanishes in the limit of vanishing temperature. Okay? So the effects of off-diagonal scattering is, you will rather see it at low voltage and small values of the parameter voltage over temperatures. Okay, it's not over, because the next step is, so now we have the quasi-particle basis in which we can compute the TBA, but the next step is also to compute the scattering matrix in this basis. So it turns out actually it's not difficult to calculate. You can define a Loschmidt echo, okay, and compute it in the two different bases, and this gives you an unambiguous determination of the boundary S matrix. Here, big R is the many-body R matrix that factorizes, and big omega is the vacuum of the algebraic beta ansatz approach, namely the state which is filled with only anti-solitons. Okay? If you do so, you can actually compute the S matrix, and it has a very simple form. It's the same as in the diagonal case, except you replace the parameter lambda by the numerator of lambda. So you see in both places, be it in the characteristics of the spectrum or in the boundary scattering, it is those elements, those objects are absolutely discontinuous at any point in lambda. So this is quite surprising. Now, at the end, you can compute the current. Okay, it's exactly the same route. So I followed exactly the same route as FLS more than 20 years ago, and you obtain a simple neat formula for this, except that now all the objects in this formula are non-continuous in lambda. So here I'll show a brief plot. If you look at the conductance, which you expect to be continuous, you can compute it from by other means. The maximal conductance is indeed a smooth function of lambda. And here in black, what I represent is for each, so obviously not all rational numbers are represented here. It's up to denominator 100. And what I plot here for each value, if each rational value with denominator smaller than 100, is the relative population of those strings. And you see that it has a very crazy structure. So this is actually quite a surprise to have such a discontinuous structure yielding continuous observable. And you notice that here there are some colored points. So I will shortly mention them. How many time do I have, Jesper? 2 minutes. 1 minute. Okay. So those corresponds to the value where experiments were conducted. So I'll briefly flash the experiments. They were conducted in the Frédéric Pierre's group close by. And what they realized the boundary sine-Gordon model with the metallic grain coupled to integer edge states of the integer quantum Hall effect. And this is the sketch of the setting. So you have different things, an ohmic contact that will set up the UV cutoff, a QPC that allows you to open or close the connection between, so this is the gamma, the impurity coupling. And you can also play with a number of edge modes that will fix the value of lambda. Okay, so I don't have time to say much about this, but actually this problem maps exactly on boundary sine-Gordon model, provided you are below the cutoff. And again, Hubert contributed to this. And in this case, that was probed experimentally, the lambda has the value 1/n with n an integer. Okay, so let me just show you those experimental results. On the left panel, you have the conductance, simply the conductance as a function of temperature. And you see that it nicely falls on those universal curves that are obtained for the cases n equals 2, 3, and 4. N equals to 1 is the free system. So here you have a fitting parameter, which is the boundary temperature. And you can even do more. You can get rid of this scale by taking the derivative of the conductance with respect to temperature. And then you get really universal curves with no fitting parameter, I mean. And in black here, you have the beta ansatz results, whereas the colored curves are the averaged experimental data. And with this, I will conclude. So I showed you an exact solution of the out of equilibrium boundary sine-Gordon model for arbitrary rational values of the parameter. It's quite complicated, the conductance doesn't see this complicated structure, and obviously it raises a question, at least I'm struggling with this question, is are those strings, those string quasiparticles, real or just an artifact of the method we use to compute the current? Thank you very much.
Okay, thank you. So we have time for a short question.
I have a comment about this. The problem was solved for any values of beta. And it is very, very simple formula, analytical formula for the currents, AC currents, for any values of beta. And its solution from differential equation, it was numerically checked, and it was given in our paper with Sasha and Volodya. And a numerical check, or Monte Carlo check of this formula was done in my work with Philippe Werner. All right. As for scattering, when you're talking about the scattering, you manipulate with some object which doesn't exist in a certain sense, because what do you think scattering of the particles is moved with the same speed of light? How you can imagine such all these mathematical structures physically seems absolutely not physical, right? So I can assign a certain sense to the basis of the scattering particles, but this is not a physical notion. That's what I'd like to say.
Thank you for your comment.
There exists a simple analytical formula for any beta, doesn't matter, rational, irrational, whatever, and it's expressed in terms of solution of differential equations, and the code for calculating this, the conductance or whole currents, it's few lines in mathematics.
Okay, I'm happy to learn it. Just for the second part of your comment, I agree that strictly in the massless limits, all particles have the same speed.
When you draw all these pictures with the particles, it means the asymptotic basis. There's no asymptotic like in quantum field theory defined. Right? To define the asymptotic basis, you need at least the particle is moving with the different speed.
Absolutely, and this you get with the big gamma, the bulk cosine potential induces a mass. And
but you see, but the boundary sine-Gordon model in which you're talking about, it's a massless path, that all the particles move with the speed of light.
I agree. I totally.
You see, this is some way to construct something, but I don't see any physical object, right? Like the particles. At the end of the day, you manipulate with the particle, with the boundary sine-Gordon, where all the particles are massive.
But we can approach this situation.
But the approach, but if you in the model, right? If you in principle, you can forget about the masses. You should formulate it intrinsically.
So may I suggest that the two of you have plenty of stuff to discuss during the coffee break, which will take place
And also the
no.
probably make a comment about the TDA equation.
Sergey, I'm sorry, I cannot cut your microphone because you don't have one, so you need to discuss during the break.